So the first thing we need to know are the rules that we're going to be working with. Here's the first one. If we have the integral from a to b of f of x dx, and we add the integral from b to c of f of x dx, that equals the integral all the way from a to c of f of x dx. Basically, if you have two integrals, they have the same function here, and they have the same bound in common, then you can basically just smush them together and go all the way from a to c. Basically what's happening here is that if we have some situation like this where we've got some curve f of x, and we've got an integral from a to b and an integral from b to c. Remember that the integral is that area under the curve. So we've got this integral right here. This is this right here, the integral from a to b of f of x dx. And this one right here that's the integral from b to c of f of x dx. And since the two areas touch, together the area goes all the way from a to c. So if we add these up, that gives us the area under the curve all the way from a to c of f of x dx. There's no gap in between, so basically we can just smush them together. The nice thing about this one is you can also go backwards. The integral from a to c of f of x dx is equal to the integral from a to b of f of x dx plus the integral from b to c. We've actually used this extensively in the past, even though we didn't realize it. If we had a shape like this, so like there's a triangle here and a semicircle or a quarter circle here, what we did in the past was we said we found this area plus this area and added them up to get the whole integral. Another rule that shows up in some unexpected ways. The integral from a to a of f of x dx equals 0. Basically what we're saying is no matter what curved shape we have, if we don't go anywhere, there's no area here. This one likes to show up in problems that look intimidating but really aren't. No matter how weird this is, no matter how much it looks like we can't take the integral of it, if the bounds are the same, the answer is 0. Doesn't matter what this is at all. Another one, the integral from a to b of f of x dx is the opposite of the integral from b to a of that same function. And this you'll have seen if you accidentally reversed the order of your bounds in any of the problems. You ended up with the same answer except it was negative instead of positive. This is also useful if we know something about the integral from b to a and we want to find something about the integral from a to b. Just making it negative reverses that order. Basically what we're looking at if we're going this way, this is a positive area. If we're going this way, this is a negative area. Sort of like if we reverse time. If we had a positive change in the antiderivative from a to b, If we're going backwards in time, we have to go back down, have a negative change to get back to our original starting position. Same thing if we have that negative area. It's negative if we're going from A to B. It reverses going the other way. Just a couple more. The antiderivative from A to B of f of x plus g of x. We've actually worked with this one already as well. We can just split up those functions. If we have a function f of x and we have a function g of x, if we put those areas on top of each other, put those functions on top of each other, so we start off with f of x, and then I put a little plus g of x, then those areas are kind of stacked on top of each other as well. And the integral under f of x plus g of x is the same as the integral under f of x plus the integral of g of x. The final one is a little bit random, but we'll put it in here for completeness. If f of x is less than g of x, always, or on the entire interval, from A to B, then the antiderivative from A to B of f of x is less than the integral from A to B of g of x. Basically what we're saying is that if we have some function f and we don't really know anything about it or about g, except that we know that g of x is always, whatever it is, it's greater than. Then when we do the integral from a to b, this area for f of x is going to be less than this area for g of x. So let's look at how to do some problems. And for these problems we have to be told something about the functions we're working with. So the key thing to notice is that all of these have the same function, and that these bounds, we have similar numbers showing up here as we do over here. So sometimes it helps to sketch it out. So we're looking for the integral from -3 to 0 We don't know what f of x looks like. It just kind of looks like that. We know the integral from negative 3 to 4. This purple area is 14. We know the integral from 0 to 4, the area under the curve from 0 to 4, is 3. And what we're looking for is this area right here, from negative 3 to 0. So what we can do, looking at this right here, is we can see that the integral from negative 3 to 0 plus the integral from 0 to 4 is going to be this whole integral from negative 3 to 4. We're told that this integral is 14. We're told that this integral is 3. And we're solving for this. So we subtract 3 from both sides. And there we go. We could also do something where we were asked find the integral from 4 to negative 3 of f of x dx. We want to know from 4 to negative 3. We currently know from negative 3 to 4, so we have to use that property right there to say this is the same thing as the opposite of the integral from negative 3 to 4. We know what that is. It was 14. So this integral from 4 to negative 3 f of x dx was negative 14. We can also find the integral from 4 to 4. As soon as we see that these bounds are the same, we know that we're not moving at all. We don't actually have any area to calculate, so it's just 0. Always if these bounds are the same. We can also do these problems if we have letters instead of numbers. That sometimes shows up. Let's find the antiderivative from 7 to 1. Or excuse me, the integral from 7 to 1 of f of x dx. So we notice up here in what we're given that this bound, the upper bound here, is the same as the lower bound here. So that means that we can put all of these together. But notice that here, the lower bound here is the same as the upper bound here. And the upper bound here is the same as the lower bound here. So we're going in the opposite direction for this one as we are up here. So we know that we can put these together to get the integral from 1 to 7. But to get the integral from 7 to 1, we have to reverse that. It's the opposite of the integral from 1 to 7. Now, make sure not to lose that negative, because in order to turn this into this, we just have to split it up. We know each of these. We're told them right in the problem, so we can just substitute in. This is 1 to 5. That's 3a minus 2b, so I can substitute 3a minus 2b in there. This is 2a plus 6b right up there, so 2a plus 6b. Combine like terms. And distribute that negative. And there we go. For our final problem, let's use the rule we haven't used yet. If the integral from 1 to 6 of f of x dx equals 13, find the integral from 1 to 6 of 2f of x plus 1 with respect to x. So let's break this apart until we have something we can do with it. Because the thing is that we know something about this f of x. We know what the value of the integral from 1 to 6 is. We've got all these other pieces around it. So we know this 2 is just along for the ride, so we can bring that here. And we know that if we have two functions added together, we can just split them apart. Now, we've got that 2. We're told that the integral from 1 to 6 of f of x dx is 13. Then we can just take this antiderivative like normal. The antiderivative of 1 is x. We're going from 1 to 6. So we've got 2 times 13 is 26, plus 6 minus, I'm just doing the substitution like we've done before. And there we go. Treating them as separate problems and then simplifying, we get 31.